This video's topic is going to be exponential equations and a few inequalities, and these are not ones yet that require logarithms. We have not discussed logarithms yet, so if that word doesn't even make sense to you, then you're in the right place. But a logarithm is how we'll solve exponentials using a calculator most of the time. It's the inverse operation of exponentiation, but for right now we're just going to solve ones that can be solved without logarithms and mostly without a calculator. So the key to this is making the bases match, and it's just very logical. You might have to do some breaking some numbers down into their prime factors, but really, if you can get the bases to match, then the exponents have to be equal. So our goal here is make the bases match. So in this first example, I've got 4 to the 2n minus 1 on the left and 64 on the right. And if I can just think of that 64 as 4 to the third, 4 times 4 is 16, 16 times 4 is 64, then all my work's basically done. If the bases match, then the exponents have to be equal. Makes sense. If 4 to something equals 4 to something else, then those two somethings should match each other. And we've got a nice simple equation. We can add 1 to both sides and get 2n equals 4 and n equals 2. Alright, so that one's kind of on the simple side, but it gets the point across. If you can get those bases to be the same, and we don't have to break them all the way down to 2. We could have broken them down till the 2 was the base, but we didn't have to go that far because we could make them match with 4 being the base. And let's move on to this next one. You should pause right now and try to solve this next one before you watch. But we're going to do basically the same thing. We've got 5 to the 5x on the left, and 125 is 5 cubed. I'm going to rewrite 125 is 5 cubed. And then our properties of exponents say that if you have a power raised to another exponent, those exponents multiply. So it's 3 times x plus 2. And now I'm basically going to get rid of my 5's. 5x equals 3 times x plus 2. In the same step, I'm going to go ahead and distribute the 3 and get 3x plus 6. Subtract 3x from both sides. I get 2x is 6 and x equals 3. Alright, so there's two nice solid examples where we make the bases match and solve the exponential equation. Alright, so here's a slight variety. We have one expressed as a fraction. So if you remember your exponent rules, basically a fraction or a number on the bottom is the same as a number on the top if it just had that exponent be negative. So 9 on the bottom is the same as 9 to the negative 1 to the 2x minus 3. And since I'm trying to make these bases match, let me go ahead and write 81 as 9 squared. These non-calculator problems, the numbers are going to be simple enough to work with to where it shouldn't be that big of a mystery what the base needs to be. If I see a 9 in the bottom and then an 81, 9's my missing link there. So with a few practice problems, it should become obvious what that base should be. Okay, so I'm going to multiply the negative 1 and the 2x minus 3 on the left. Basically, the 2x will become negative and the 3 will become positive. And I'm going to multiply the 2 by the x minus 4, which gives me 2x minus 8. And I have another linear equation. I add 2x to both sides, making 4x on the right. I'm going to add 8 to both sides, giving me 11 on the left. And divide by 4, I'm going to get 11 fourths. Alright, no calculator necessary, 11 fourths. Alright, so we're going to mix it up a little bit and now do an inequality. Now an inequality is going to work exactly the same except with one technicality. I need my base to be bigger than 1. Because when the base is a fraction, a number between 0 and 1, the exponential function works differently. It decreases. As long as the base is bigger than 1, I can do exactly how I can do the exact same process, except I'll have the inequality symbol in between instead of an equal sign. But let's do the same thing we've been doing. Now 64 is 4 to the third. So 3 times 2x minus 4 is 6x minus 12. And since the bases match, and since the base is greater than 1, I can just drop the base. And now I've got a nice simple inequality. Let me see, I will subtract 2x from both sides, giving me 4x on the right. And I will add 12 to both sides, giving me 18 on the left. Divide by 4. And I never divided by any negative, so I don't need to flip my sign. X is greater than or equal to 18 fourths, or 9 halves. Alright, so as long as the base is bigger than 1, then nothing's going to work any differently. I just have an inequality instead of an equation. Here's the reason why the base needs to be bigger than 1. If your function has a base bigger than 1, like the blue graph, like y equals 2 to the x, it's increasing. So if I just drop my 2 bases, basically it's telling me, if the exponent's bigger, then the whole value will be bigger, which is just what allows us to just drop them. If the base happens to be a fraction like 1/2, then the function is decreasing as we move left to right. So we've got a couple options when something like this pops up. We could solve it in either way. We'll just flip the sign if we decide to go with the fraction. Let's check out an example. Okay, so we've kind of seen stuff like this before. If we wanted to do this one and keep the base bigger than 1, like we've been doing, let me call this 4 to the negative 1 to the 2x plus 3 greater than or equal to 16 to the 3x. Actually, let me go ahead and save a line and call that 4 squared to the 3x. And my bases are going to match, and they're both going to be 4s. So 4 to the negative 2x minus 3, which is what I get when I multiply negative 1 by that other exponent, and then 4 to the 6x on the right. So since my bases are both bigger than 1, I have negative 2x minus 3 greater than or equal to 6x. If I add 2x to both sides, I get 8x on the right. Negative 3 divided by 8, divide by 8. And negative 3/8 is greater than or equal to x. So let's say, if our one option is to just not have a fractional base to the power, and instead of thinking of it as 1/4, we think of it as 4 to the negative 1. That's always a good option. And just for our discussion, and in case this ever happens to pop up, let's work it the other way. What if we decided to make 1/4 the common base? 2x plus 3. And now 16. If I want to express 16 as a power of 1/4, it's 1/4 to the negative 2, right? Because the 2 would make it 16, and the negative would flip it up to the top. So it's 1/4 to the negative 2 to the 3x. So now I can drop my bases. This base is 1/4, which is not bigger than 1. And we'll see what happens. 2x plus 3 greater than or equal to negative 6x. All right. So now let's see. I will subtract 2x from both sides and get 3 is greater than or equal to negative 8x. I'm going to divide by a negative 8. And whenever I divide both sides of an equation by a negative, an inequality by a negative 3/8, I have to flip my sign, and I get x is greater than or equal to negative 3/8. Well, we've already determined from earlier that x is less than or equal to negative 3/8. Okay, so if you go with the fractional base like 1/4, then you needed to flip it from the get-go. We needed to point this sign the other way and make it less than or equal to all the way down. So when I flipped it, I'd flip it back the other way. So you've got two options. Either worry about that or just never let your base be a negative. All right, but most importantly, I just want you to understand why, according to these exponential functions, if it's a fractional base, that it doesn't work to just drop that base. All right, because fractional bases create functions that are decreasing as we move left to right. We would have to flip the sign to solve that inequality.